This video was developed by the U.S. Department of Energy's National Energy Technology Laboratory as part of a larger effort to share information about carbon sequestration, which is an important part of a portfolio of technologies that could be used to reduce greenhouse gas emissions like CO2. Greenhouses are warm because heat from sunlight passes through the glass and then gets trapped inside. Greenhouse gases in the Earth's atmosphere, like water vapor and carbon dioxide, or CO2, act much like the glass in a greenhouse. As you can see in this image, light from the sun passes through the atmosphere like it does through glass in a greenhouse. In our atmosphere, this light heats the air and the surface of the planet. Some of that heat gets radiated back out through the atmosphere, and some of it remains trapped. Life as we know it depends on this natural heat-regulating function, since it keeps our planet livable. There is concern that as levels of greenhouse gases increase, our atmosphere may trap more heat than we need. This could lead to changes in climate and weather around the planet that are commonly referred to as global climate change. Since the Industrial Revolution began, man-made CO2 emissions, mainly from the use of fossil energy, have increased significantly. Without action, these annual emissions will become even larger as population grows, and development gives millions of people around the world access to reliable energy and transportation. Without major changes, it's expected that by the year 2050, the world will go from emitting about 23 billion tons per year to emitting about 53 billion tons per year. Since CO2 and other greenhouse gases stay in the atmosphere for so long, the emissions from today will have an impact on greenhouse gas concentrations in the atmosphere long into the future. Large reductions in emissions will be needed soon to address climate change. The U.S. Department of Energy has supported a broad array of research on climate change. These technologies can be placed into three categories: energy efficiency, renewable energy, and carbon sequestration. These technologies are the three pillars of the Global Climate Change Initiative announced in February 2002. One study conducted in 2004 showed that these three technologies are key in avoiding increases in future emissions, holding them flat in the U.S. through 2050. This graph illustrates the results of that study. The top blue line shows projected U.S. CO2 emissions between 1990 and 2050. The flat brown line shows what emissions would look like if they were held flat through 2050. The gap between these two lines is equal to a reduction of 5.3 billion tons of CO2 emissions in the U.S. by 2050. That is almost as much as the United States puts in the air right now. Improvements in energy efficiency and the use of renewable energy sources, along with improvements in auto efficiency, use of alternative energy sources, and reduction in agriculture emissions, can account for nearly two-thirds of this gap, as seen in the yellow and green wedges. But even with significant investment in renewable energy and efficiency, these two technology options will not be enough to stabilize greenhouse gas emissions. Carbon sequestration is a promising technology that has the potential to significantly reduce CO2. As the light blue wedge shows, CCS has the potential to help meet the gap in emissions reductions. CCS is the term used to describe a broad group of technologies for capturing and permanently sequestering or storing CO2 in biologic materials like trees, or in deep underground geologic formations like oil fields, unminable coal seams, and deep saltwater geologic formations. The techniques used in CCS are already in use today in a process called enhanced oil recovery. In this process, CO2 is injected into an old oil field to help recover oil that would have otherwise been left behind. You probably know that plants take in CO2 from the air and store part of the carbon in leaves, stems, and in the soil. But you may not have heard of geologic storage, an approach that holds tremendous promise to store CO2 rather than being released to our atmosphere. In geologic storage, CO2 is captured from large fossil fuel users like power plants before it can enter the air. The CO2 is transported to the injection site, where it is pumped several thousand feet below the surface into layers of porous rock, such as sandstone, that are located under layers of tight, non-porous rock called caprock. The rock formations into which CO2 is injected are porous, like this sandstone. If you looked at sandstone like this under the microscope, you would see that there are spaces known as pore spaces throughout the rock. In this view, the pores have been filled with blue dye to make it easier to see them. In this view, water is being dripped onto the sandstone, and you can see it moving into the pore spaces. CO2 injected into these porous sandstone layers deep underground are contained by several layers of impermeable rock, called caprock, above the injection zone. Caprock acts as a seal preventing the CO2 from moving to the surface. This is the same kind of seal that has kept oil and gas in storage in natural reservoirs for thousands of years. As you can see here, the impermeable rock that forms a cap is very different than porous sandstone where injection takes place. The pore spaces in the impermeable rock are so small that there is very little room for CO2 to move into. As you can see in this magnified view, there is very little pore space in the caprock compared to the sandstone we saw earlier. Here we compare two magnified views of pore spaces. Both images are taken using the same magnification, and the pore spaces in both are filled with blue dye to make it easier to see them. As you can see, the water being dripped onto the impermeable rock simply pools on the surface and does not penetrate. And now look at the difference between the movement of water dripped on the two types of rock. The porous sandstone acts like a sponge as the water moves into its pores, while the water on the caprock is unable to penetrate the rock and runs off. In CCS, CO2 is pressurized so it becomes like a liquid and is then pumped into a porous rock layer. Because the well is located so deep underground, the natural pressure of the rock layers above it keep the CO2 in a semi-liquid state. Once injected, it very slowly spreads out into the pore spaces of the rock layer and dissolves into the salty water or brine, which is found in the very deep layers of rock formations. Research is underway around the world to determine how to safely and cost-effectively use CCS to address climate change. Today there are a handful of large-scale CCS operations, and there are numerous research and development projects. In the United States, research into CCS is overseen by the Department of Energy. It consists of a core research and development program and the Infrastructure Development Initiative, which includes a network of regional carbon sequestration partnerships. These 7 partnerships represent over 300 organizations working to characterize their region's potential sequestration opportunities, research the infrastructure needed to deploy CCS technologies in North America, and validate the most promising opportunities in their regions. These partnerships will play a key role in getting CCS technologies out in the field. For more information on CCS and the DOE programs, please visit the NETL website.